So this is going to be chapter 6 of section 7, which is basically going to be kind of capping off this similarity stuff we've been talking about. So we've done a lot with similarity between triangles before, and it's mainly been two different triangles. And it's been stuff like, this side is proportional to that side, and this angle is congruent to that angle. So we're going to be talking about three segments here that are also proportional, but aren't directly related to like the sides of a triangle. So the first one are altitudes. So altitudes in a triangle, we're first just going to briefly go over what they are before I talk about how they're similar. So the altitudes are basically, if you have a triangle, you take a segment from one corner directly to the other side, and you make sure that it's a perpendicular line. So the segment that's perpendicular from the point of a triangle to the opposite side is what's called an altitude. And again, you can have altitudes from any point. So I could have this right here. As long as it's a right angle, that'd be an altitude. So altitudes can go from any point. They always go to the opposite side, and they're always perpendicular. Angle bisectors are just like they sound. You take any angle in a triangle and you draw a segment so that it cuts it in half. So draw like this, and then as long as this top angle is congruent to this bottom angle, that's an angle bisector. And again, you can go from top or the other side as well. You can go from any angle you want as long as the line bisects it. Now notice that this does not have to be perpendicular. So an altitude is not necessarily an angle bisector, although it could be. If for some reason you had a line that went from here to here, that was perpendicular and it cut the angle in half, then this would be both an altitude and an angle bisector. So these segments are not necessarily all the same line, but they could be if a certain triangle is made that way. And then finally, a median is simply a segment that goes from one vertex to the other, as usual. Oh, that's an ugly triangle. Let me try that again. It goes from a vertex to the opposite side, and it's not a right angle necessarily, and doesn't necessarily bisect the angle, but it does cut the opposite side in half. So it does attach at the MP, or the midpoint of the opposite side. And once again, if I draw a segment like this in a triangle, it might be an altitude, it might be an angle bisector, it might be a median, it might be all three, it might be two of the three. We don't know until we have the information. But these segments can all be the same segment, or they can be three different segments. Just depends on the triangle. So, come on. These segments are all similar when dealing with similar triangles, so they behave just like sides. So for instance, if I have these two triangles, and I told you that these are similar triangles because they have two pairs of angles that are congruent, so we know that they're similar by the AA theorem, that means that this side to this side, so notice it goes single arc to non-arc, single arc to non-arc, so 20 is to 15 as, and then it's, in this case, this is an altitude because they're at right angles. So 20 is to 15 as 16 is to x. So side to side, altitude to altitude. And then you just simply cross multiply. So you have 20x is equal to 16 times 15, which is 16 times 15, 240. Then you divide by 20, and you get 12 is equal to x. So the way you solve these is just like we did in the last videos. You solve them just as if they were the side of a triangle. You have your scale factor fraction first, and you get this by using whatever you can in the triangle to link up. So you use the corresponding pieces there. So we used single arc to non-arc side, single arc to non-arc side. We put them as a fraction. And then we did altitude to altitude, put that as a fraction, and cross multiply. And again, we're always consistent. So if this was triangle 1 and this was triangle 2, we did triangle 1 over triangle 2. This was triangle 1 over triangle 2. So again, always be consistent with how you set up your fractions. And this works for medians, it works for angle bisectors, and it works for, as it says here, altitudes. So it works for any of the three segments we just did. So in this case, we have what looks to be medians, right? And angle well, that's just one big arc over the entire angle, so we don't know it's an angle bisector. But we do know it's a median. So TP and WQ are both medians of their respective triangles because they go from a corner and they split the opposite side in half. So they're medians. So once again, because they're both medians, they have to be proportional to each other just as all the other sides are. So median to median, so 13.5 to 9, is going to be the same as side piece to side piece. So x to 3. So even though it's not the entire side length, cutting it in half preserves the proportionality. So we can just use the individual pieces if we want to as well. So now we can go ahead and cross multiply. So we get 9x is equal to 13.5 times 3, which I could probably do in my head, but don't feel like. Whoops. There you go. 40.5. And then divide by 9. And we get x is equal to, divide by 9, 4.5. So once again, treat them, angle bisectors, medians, altitudes, treat them just like you would the sides of similar triangles. If the triangles are similar, then the altitudes, medians, and angle bisectors are similar with their corresponding pieces as well. So you can use them to set up a scale factor fraction as well as use them to get solved for. Now, angle bisectors are special in that they also have a proportionality within the same triangle. So, for instance, if I take this triangle and I draw an angle bisector, so it's an angle bisector, and we'll say that this top angle is congruent to this bottom angle because it is an angle bisector. Let me put some labels here. We'll call this A, B, C, and D. What happens here is that these two segments are in the same proportionality as these two segments, these two legs here. So to put that in sort of math speak, to put it in sort of a numerical way, I can say that, let me get my pen here, I can say that AB is to, let's see here, AB is to AD as BC is to DC. Or I should, let me be consistent and say CD, just so I get my lettering consistent. Come on. Ah, can't click this. CD. So this piece to this piece is the same as this piece to this piece. So the individual pieces of the two sort of sub-triangles being made are in proportion to each other. And you can switch this around a little bit too. You can play around with it. So this also means that, you know, I can say that AB is to BC. So top is to bottom as long leg here, AD, is to long leg here, CD. So split is to split as side is to side. That's also another proportionality that comes through here. So you can mess with this fraction any way you want, really, for the most part. But these are the two most common ways to set it up: is split piece to long piece is to split piece to long piece, or split is to split as long is to long. As long as you're consistent with how you set up your fractions, once again, you're okay. So basically, think about these as two separate triangles. So this top one would be triangle 1, this bottom one would be triangle 2, and that they're kind of similar to each other in a sense. They're not really, but we'll just assume that they're similar, just to make sure that the fractions are easier to get, if that helps you. So let's take this and see if we can't mess with it a little bit. So if I have this triangle, this is obviously an angle bisector because it splits this angle in half. And again, this only works if you have an angle bisector as your midline. So it doesn't work for medians or altitudes. This is only for angle bisectors. So that means that I can do split is to split. So 4 is to 6 as long is to long. So as x is to 13. And then you cross multiply. So 4 times 13 is going to give me, that'd be 52, is equal to 6x. Divide by 6. You got 4 times 13 divided by 6. We get 8.6 repeating is equal to x. So once again, split is to split as long is to long. Or just to show you, you could set up like this. Let me erase this here. This might be an easier way for some of you if you don't like that. You could set it up as split is to long as split is to long. So you could set up as 4 is to x as 6 is to 13. And if you notice, you end up cross multiplying the same things. X times 6 and 4 times 13. So here, x and 6 got multiplied together. Here, x and 6 got multiplied together. Here, 13 and 4 got multiplied together. Here, 13 and 4 got multiplied together. So again, as long as you're consistent with how you set up, there's a few different ways you can go about it. Now, 3b here is a little bit tricky because they have the entire side length as 20. So our fractions, remember, are, let's do the way we just did there, is split with long, split with long. But I don't know how big this split is here. My first fraction is pretty easy to get, x over 14. That's good there. But this next fraction, I don't know what this side is here. Well, think about this for a minute. If the entire thing is 20, I know that this piece over here is x. That means this is whatever's left over. So this piece right here is 20 minus x. So that's the length I'm going to go with. So I'm going to say 20 minus x, which is basically whatever's left over after I get the x part here, is to 11. So if you know the entire length and you know at least one segment, you can get the other segment by simply saying it's the entire length minus the piece that I already knew. Like, for instance, if this was 5, then we know that this would be 20 minus 5 or 15. That way they'd add to 20. So I don't know if this is 5 or not, but I do know it's x. So I can just replace 5 with x and set it up the same way. Now I can cross multiply. Remember, when you cross multiply with a two-term thing like 20 minus x, you multiply it to both terms. So 14 times 20 and times x. So 14 times 20 is 280. Times x would be minus 14x. And then here we have 11x. So now I'm going to add 14 to x to both sides to get the x's on the same side. So I get 280 is equal to 25x. Divide by 25, and we get x is equal to 280 divided by 25, 11.2. And that is how big x is. So if they give you the entire length, don't forget that subtraction trick to help you figure out that missing piece you need so that you can set up your fraction. Because remember, you need that split piece in order to make your fraction work. Now let's try a few more of these before we end the video here. So these segments right here are not angle bisectors. If you see that this angle isn't said to be cut in half. These angles are not cut in half, so we can't assume that they're angle bisectors. But they are medians because they split the opposite side in half. So because they're medians, we can go ahead and set up the same fraction we did earlier in the video. So side piece to side piece, so 12 is to 15, as median is to median. So x is to 10. And then cross. So 120 is equal to 15x. Divide by 15. And we'll get x is equal to, that would be 80, or 8, right? 120 divided by 15 should be 8. Yeah. I could do it in my head. So that would be how big x is. So again, medians, altitudes, and angle bisectors, you can always use two triangles as well. It's just that for the angle bisectors, they have this little sub trick here. When you have one triangle and an angle bisector in it, you can do this little trick here to figure out the missing pieces. But when you have two triangles, it's just like what we did earlier in the video, the very first problems we did in this video. Just like this one here. These are two altitudes, right? Because they make right angles here and here. So they're two altitudes. So once again, we have side to side, 8 to 6, altitude to altitude, x to 9. And again, I'm always going from triangle 1 to triangle 2, triangle 1 to triangle 2, being consistent. So cross and cross, 72 is equal to 6x. Divide by 6, that's 72. X is going to be equal to 12. Right. So that's it for this video. Again, there's just going to be a few similar tricks on triangles there. There's basically two types of problems we went over here. We went over the types of problems in the very beginning of the video where you have two different triangles and you have medians or angle bisector segments between them. And then we went over when you have one triangle with one angle bisector and how to get different pieces within that same triangle. So if you notice in these problems, 3a and 3b, we only had one triangle that we had to figure out a missing piece for, whereas in the other problems, we had two triangles that we're trying to figure out a missing piece in one of them for. So make sure you review these two problems, notice how they're different, notice what to do that's similar, that way you don't get them mixed up. Hope you enjoyed the video. Have a good day, night, or afternoon.